Welcome back to TalkTensors, everyone. Today, we're diving deep into, deep reasoning, or rather, how to evaluate it in these increasingly complex, multimodal, large language models. The ones handling both text and images.
Right, and particularly when these MLMs are tackling scientific problems. It's one thing to get to the right answer, but the path they take to get there, the reasoning itself, that's what we really need to scrutinize.
Exactly, because as these models become more sophisticated, it's getting trickier to tell if they're genuinely reasoning or just, really good at spotting patterns in the data, which might lead them to the correct answer, but through faulty logic.
And that's precisely where this paper we're looking at comes in. ProJudge, a multimodal, multidiscipline benchmark and instruction tuning dataset for MLLM-based process judges.
Catchy title, right. But it gets right to the heart of the matter. Can we use AI, other MLLMs specifically, to judge the reasoning process of these AI problem solvers? And if so, how do we make sure those AI judges are actually reliable?
It's a meta problem, judging the judges. And this paper tackles it head on. First, by identifying the shortcomings in existing benchmarks for evaluating these MLLM-based process judges.
They point out three main issues. One, the narrow scope of a lot of benchmarks, meaning they focus on just text or just images, or they stick to one scientific field or look at relatively simple problems.
Right, and that doesn't reflect the kind of multifaceted reasoning we see in real-world scientific problem solving.
The second issue is insufficient error analysis. A lot of benchmarks just flag errors. They don't really break down the type of error being made.
Like, is it a calculation error?
Yeah.
A misinterpretation of the visual data, a logical fallacy. Knowing the kind of error is essential for figuring out where the model is going wrong.
Absolutely. And then the third problem with existing benchmarks is the data itself. Often it's either synthetic, like artificially generated errors, or it's not generalizable, so it only works well for very specific models.
Which makes it hard to confidently say whether a process judge would perform well in a more diverse, real-world setting.
So to address these limitations, the authors introduce ProJudge Bench.
It's really designed to be a far more comprehensive and realistic benchmark for evaluating process judges. And they hit that multifaceted aspect we were talking about earlier.
So multimodal, right. It includes both text and images in the problems.
Multidiscipline as well, covering maths, physics, chemistry, and biology.
And multi-difficulty. So problems ranging from K-12 level all the way up to competition level.
And the scale of ProJudge Bench is impressive. We're talking 2,400 test cases, broken down into over 50,000 individual steps, each one annotated by human experts.
And that's where the fine-grained error analysis comes in. They don't just say, okay, this step is wrong. They label the specific type of error.
From a list of 7 they've defined, like reasoning errors, visual interpretation errors, calculation errors, the whole gamut.
And critically, the solutions they used to build this benchmark came from 10 different MLLMs.
So they're capturing a really diverse range of error patterns, the kind you'd actually expect to see in the wild, so to speak.
Yeah. Not just the quirks of one particular model. When they tested 11 different MLLMs using ProJudge Bench, they found a pretty clear performance gap. Proprietary models, like the ones from OpenAI and Google, were outperforming the open source models when it came to evaluating reasoning.
So then they set out to, bridge that gap, which brings us to ProJudge 173K and their dynamic dual phase fine-tuning strategy.
ProJudge 173K is a massive data set they created specifically for training MLLMs to become better process judges. It's all about teaching them how to evaluate reasoning effectively.
And they built this data set in a couple of clever ways. The first is what they call controlled error injection. So they took correct solutions and intentionally introduced specific types of errors.
Using GPT-4o, which is, one of the big players in this space.
Exactly. So they knew exactly what errors they were putting in and why. For the second part, they did realistic error collection, similar to how they built ProJudge Bench. They had 9 different MLLMs try to solve problems from competitions in K-12 material, then used GPT-4o to evaluate each step, get the error types, the whole 9 yards.
So a combination of carefully controlled errors and real-world errors that models actually make. And then, of course, they did a bunch of filtering to make sure the data was high quality and consistent.
Now, for the fine-tuning strategy itself, the dynamic dual-phase approach, it's really about training the judging model in 2 different but interconnected ways. The first phase, direct evaluate, is pretty straightforward. The model looks at the problem, the student's solution, and the expected final answer, and has to judge each step.
Okay, makes sense.
But the second phase, synthesize then evaluate, is where things get more interesting. In this phase, the model first generates its own solution to the problem, and it's actually given the correct final answer to help guide it.
So it's going through the reasoning process itself before it even starts judging the student's solution.
Exactly. It's kind of like how a human expert would grade, right? You wouldn't just look at the answer. You'd work through the problem yourself first to understand the concepts and the steps involved.
And then the dynamic part means the model is switching back and forth between these two phases during training.
Which helps it generalize, become more adaptable to different kinds of problems and different reasoning styles.
And did this DDP approach work?
Oh yeah. They saw significant improvements when they fine-tuned open source models, like Intern VL 2.5 and Quinn using ProJudge 173K and DDP.
Like how significant?
In some cases, these fine-tuned open source models were even outperforming larger base models that hadn't gone through this specific training.
So closing the gap on the proprietary models, which is a big deal for accessibility and open research. Now, what about the overall results they got using ProJudge Bench? What did we learn about how well these models can judge reasoning?
Well, as you might expect, larger models generally do better, which isn't too surprising. And as we mentioned earlier, proprietary models still have an edge in performance. But that gap is shrinking thanks to these new techniques. What's also interesting is they found that different models have different strengths when it comes to spotting specific types of errors. Some are better at catching calculation mistakes, others are better at flagging logical fallacies, and so on.
And how consistent is performance across different scientific fields?
They saw some variation there. Performance tends to be higher in biology and chemistry compared to math and physics.
I wonder why that is.
Yeah, it's an open question, definitely worth investigating further. And they also found that performance drops off as problem difficulty increases, which again is pretty intuitive. Open source models in particular really struggle with problems involving images, so that visual reasoning aspect is still a challenge for them.
Interesting. Did they find anything else about how these models judge reasoning?
Well, one curious finding is that models tend to do better when they're evaluating solutions from models that are architecturally similar to them or even smaller.
So they're more accurate when judging their peers or their juniors, so to speak, almost like there's a bias toward reasoning processes they're familiar with.
It's a possibility, and something that definitely warrants further exploration. Another interesting finding is that there's a noticeable difference between how well models can generate errors versus how well they can detect them. So certain types of errors, like visual interpretation errors, they happen a lot when the models are solving problems. But those same errors are often missed by the models when they're in judging mode.
So there's room for improvement on both fronts, both in avoiding those errors in the first place and in being able to reliably catch them.
Precisely. And their analysis of the DDP fine-tuning strategy showed that it was really effective, especially when it came to helping models generalize so they could accurately judge reasoning on problems they hadn't seen before.
Makes sense. Now, to put all of this work into context, let's take a step back and think about how AI evaluation has evolved over time.
Sure. In the early days, it was all about simple accuracy metrics, right? How many times does the model get the right answer?
But as models started doing more complex tasks, we realized that final answer accuracy wasn't enough. It didn't tell us how the model got there, whether the reasoning was sound.
And that led to the development of benchmarks, especially in fields like math, where the reasoning process is so crucial. MMMU and MathVista are good examples of this, but they still mainly focused on the final answer.
So ProJudge really builds on this need in the ML community to move beyond just looking at the output and really scrutinizing the reasoning itself.
And this shift toward using LLMs to evaluate other LLMs, it's really a natural progression, wouldn't you say?
Oh, absolutely. As these models get more complex and the data gets bigger, it's just not feasible for humans to do all the evaluation.
So we need AI judges, but they have to be trustworthy. And that's what this work is all about.
Okay, so let's recap the key takeaways for our listeners. This paper gives us ProJudge Bench, a much-needed, comprehensive, and realistic benchmark for evaluating how well MLLMs reason through scientific problems.
We also have ProJudge 173K, this massive data set for training process judges, along with a dynamic dual-phase fine-tuning strategy, which has been shown to dramatically improve the performance of open-source models.
And the research provides valuable insights into the current strengths and weaknesses of MLLMs, both when they're solving problems and when they're acting as judges.
And that detailed error analysis, looking at what kinds of errors models make and how well they detect them, that's essential for guiding future research, helping us build AI systems that are more reliable and trustworthy.
Now let's move into our novel notions segment, where we riff on some potential research directions inspired by this paper. So one thought I had was, what if we tried to fool these MLLM-based judges?
You mean like create adversarial examples?
Exactly. But instead of trying to trick the problem-solving model, we'd be targeting the reasoning evaluation process itself.
So like crafting reasoning, that seems perfectly logical at first glance, but actually contains subtle flaws, specifically designed to slip past the judge's detection.
Right. If we could successfully do this, it would expose vulnerabilities in how we're currently evaluating reasoning. It would force us to think about, like, what are we missing? What are the blind spots in our current methods?
It'd be like a stress test for these process judges, pushing them to their limits.
And for our second novel notion, what if we tried to build a self-evaluating MLLM? So the model would not only try to solve the problem, but at each step, it would also analyze its own reasoning and try to catch any errors.
So basically, building in a kind of metacognitive ability, a capacity for critical self-reflection.
Exactly. And this could lead to more reliable AI systems overall, right? Because they wouldn't be so reliant on external feedback or evaluation. They'd be constantly checking their own work, becoming more robust and trustworthy over time.
Now, as always, we should emphasize that these are just speculative ideas, and the actual feasibility and outcomes could be quite different. But I think they highlight the potential for building upon this research and pushing the boundaries of how we understand and evaluate AI reasoning.
Absolutely. To wrap up our deep dive into this fascinating paper, the work on ProJudge underscores the critical need to evaluate not just the answers AI provides, but also the reasoning behind those answers, especially as these systems take on more complex scientific challenges.
And as AI becomes more deeply integrated into our lives, being able to trust its reasoning processes will be just as important, if not more important, than trusting its final outputs.
So, a question for our listeners to ponder. What are the most promising paths forward for creating more reliable and transparent AI reasoning systems? And how can we build on work like ProJudge to get there?
It's something to think about.
As always, the link to the full paper is in the show notes for those who want to explore the details further.
Thanks for joining us for this deep dive into cutting-edge machine learning research. We'll see you in the next episode of TalkTensors.
See you next time.